So today we're gonna work on this worksheet number 9 about parametric curves, and we have 3 questions here. Or actually, we also need to deal with improper integrals. So we will do with those improper integrals for the first 2 questions, and the third question we're gonna do those parametric curves. So the first question, determine whether the given integral is convergent or divergent. Evaluate those that are convergent. So let's work them out. Now we deal with this question A here, right? So when we have this integral, we look at the denominator here, because this is a rational function, right? We know that when x is equal to 8, the function is not defined. So the only problematic point here is this point, x equal to 8. So to evaluate this limit, we just need to turn that into the to evaluate this integral, we just need to turn that into the limit notation. So that is t goes to 8 minus, right? Because that's at the left hand side of 8, and this turns to integral from 0 to t 8 minus x to the negative 1/3 dx. Okay. And you can use substitution to work this out very quickly. Let me just write it down here for you. So we can change this to d negative x, right? By placing a negative sign here. Okay. That's negative x. And also there's no harm to plus and 8, right? So we can plus and 8, so or maybe plus the 8 here. So now they're the same. This is 8 minus x. This is also 8 minus x, right? So now this becomes 3/2, 8 minus x to the 2/3, right? Times that negative 1. The negative 1 is of course here. This one, t0, right? It's this one here. And if you plug in, then you have limit t goes to 8 minus, right? This is negative 3/2, 8 minus t to the 2/3 minus 8 to the 2/3. Right. Now look at this expression. This expression is the square root of the cube root of 3, right, to the square, right? And then t is going to the left side of 8, so 8 minus t is greater than 0, or even is less than 0. It does not matter because this is a cube root, right, not a square root. So under any circumstances, this is defined, and then we just plug in. So we have 0 minus 4, which is equal to 6, right? That is how we evaluate this improper integral. It is convergent. Because we are able to compute the answer. Okay, now you see that to evaluate an improper integrals, one of the ways is to turn that into the limit notation, And before we do that, we also need to recognize the potential points, right? The singular point. In this case, that is 8. And apart from that, there's nothing new here. So that is our question A. And now move on to this question B. So now, as before, we want to recognize the singular points first, right? Tangent pi is defined, right? The only place the tangent x is not defined is this place at pi over 2. So as long as we recognize it, we can turn that into the limit notation. This time it's going to be t goes to pi over 2 plus, because the interval is from pi over 2 to pi, so t should be greater than pi over 2. So this is going to be from t to pi tangent x dx, right? Now we can look up to our formula sheet to find out what this integral is. Right? This integral is ln negative ln this cos x, right, pi t so that is from our formula sheet. I mean, from this step to this step in the formula sheet. Okay, and after this we can plug in, right? So plug in, we have limit t goes to pi over 2 plus of this negative ln of cos pi, right, plus ln of cos t. And of course the first one there, that is equal to, I mean this one, cos negative pi, that is cos pi is equal to negative 1, and absolute value brings that to positive 1, right? So ln positive 1, that is 0, right? So we're purely dealing with the other guy here, that is this one, right? This one, when t approaches pi over 2, cos t is going to be 0, right? Cos t is going to be 0. So we are looking at ln 0. ln 0, what is it? That is negative infinity, right? So this guy goes to negative infinity. Okay, so the final answer is negative infinity. Right? That's our final answer. It's not a finite limit, and therefore the answer is divergent. Okay, and you see that is exactly the same as the previous question, except for the fact that this is not a finite limit. But there's nothing more than recognizing the singular point and turning that into the limit computation and then figure out the integral. Okay, that is our question B. Now move on to this question C here. This is a rational function inside the integral, right? And we see that the function is not defined when this square root of x minus 2 is equal to 0, right? That is when x is equal to 4, right? This is not defined. And we also notice that this singular point is inside our interval from 1 to 9, right? So this singular point, we have to consider it, okay? So to consider it, we need to first break this into two integrals, that is from 1 to 4 of this, right, plus from 4 to 9 of this, and then we deal with the singular points at each of these integrals. So if both of these integrals are convergent, then this integral is convergent. And if either of this one is not convergent, then this whole thing is not convergent. So the idea is very simple here. Right? So we need to evaluate this guy first. So as soon as we recognize the singular point, we want to turn that into the limit computation. So I want to figure out the indefinite integral first, and then after that I will plug in. So let's figure this out. Indefinite integral, right? This guy is equal to, right? If you let, for example, u equal to this square root of x minus 2, then you have x equal to u plus 2 squared, right, by moving the terms, and then dx here should be 2 times u plus 2 du. Right? That is our substitution we need here. So that becomes top, we have u here, 1 over u, right? Dx is 2 times u plus 2 du, right? And this is very simple, just 2 plus 4 divided by u du, which is 2u plus 4 times sine ln of u plus c. And we are going to substitute back the u with square root of x minus 2, and it finally becomes 2 times square root of x minus 2 plus 4 ln of square root of x minus 2, right? And plus c, where c is any real numbers. Okay, now we've got what we need, the indefinite integral in here, right? The reason we need it because we need to turn that into the limit notation. Okay, so now this thing 1/4 of this definite integral can be written as limit t goes to 4 minus, right, because 4 is the singular point, from 1 to t of this one dx, right? And according to the green formula, okay, the green formula, we can change the definite integral there to that function that is 2 times square root of t minus 2 plus 4 ln t minus 2, right, of this one. So let me write that here, right? This one here, with the upper bound t and the lower bound 1. And we kind of plug in after that 4 minus, so this will become, oh sorry, this should be x, this should be x minus 2x. Okay, and then we now plug in So plug in, we will have 2t minus 2 plus 4 ln square root of t minus 2, right, absolute value. This one minus the plug in 1, we have 2 times, this is 1 minus 2, right, and then plus 4 ln 1 minus 2, like that. Gigantic expression, but it finally can be simplified to 2 square root of t minus 2 plus ln 4 ln square root of t minus 2 plus 2. That is for just for the last part there, the constant. Okay, so now we can start to work on the limit, right? The limit of the first guy here is 0, right? This one is 0. And for this one is constantly 2, right? But for the middle one here, right? For the middle one here, that is when t goes to 4, we have 4 a square root of 4, that's equal to 2. 2 minus 2 is equal to 0. So ln of 0, that is the thing we're looking at. Well, ln of 0 is negative infinity. Right, so the middle guy here is negative infinity. And therefore, its integral is equal to negative infinity. Right? Which means it's divergent. Right? Divergent. And because one of it is divergent, so the whole thing is divergent. So this from 1 to 9, this guy, it's divergent. That is also very simple, except for that we need to break down this function into 2 definite integrals. That is the only difference between this and the previous questions. And apart from that, there's nothing new, right? There's nothing more than turning that into the limit notation and computing the limit. Okay. And that is our question C. And now, maybe go to question D here. Question D here, we have from negative infinity to positive infinity of this function, right? And what do we want to do here? So we have both infinity at lower bound and upper bound. And at this case, regardless, we will need to break that into two integrals. That is from negative infinity to 0, right? Dx plus this from 0 to positive infinity, because we can only have one bounds being infinity by the definition. And that point, splitting point, is not necessarily need to be 0. It can be 1, 2, 3, or anything you like. But you know, for simplicity, we just put 0 here. But that does not mean it has to be 0. The thing is that we only allowed one bound being infinity. Okay, so that is the thing. And after this, we need to evaluate each of these integrals, right, to determine whether the function is convergent or not. And same as the previous question, if both of these are convergent, then the sum is going to be convergent. Otherwise, one of this being divergent means the whole thing is divergent. So now let's work on the definite integral first, indefinite integral first. So this one, right, becomes 2x squared bracket plus 1 dx, right? So that turns into the tangent function, right? The tangent function, you know, we can change this to d of, you know, 2x and put a 1 over 2 here. Put a 1 over 2 here, right? So now you make use of that formula, that tangent inverse formula, right? And then this becomes tangent negative 1 of 2x, right? This 1 over 2. And then it becomes, this is plus c, where c is any real number. So that's the original function. And after having this, now I can write this limit, the first integral from negative infinity to 0, right? This into the limit notation, limit t goes to negative infinity of this from t to 0 for x squared plus 1 dx. And now we substitute the integral with the function we just found, that is the original function, 1 over 2 tangent inverse 2x, right? Lower bound and upper bound being 0 and t. Okay, and now compute this. This becomes the plug in 0, we get 0, right? And plug in t, we get 1 over 2 tangent inverse this 2t, right? And by the property of the inverse function, when t goes to negative infinity, this guy goes to negative 1 over 4, right? So this is 0 minus 1 over 2 times this 1 over 2, 1 over 2 pi, which is 1 over 4 pi. Now the answer is negative 1 over 4. Fix that. This is negative of that one. 1 over 2 times negative 1 over 2 pi. Okay. And then it becomes negative of negative 1 over 4 pi is positive 1 over 4 pi. Okay. If you're not familiar with what this is, you can look up the graph, right? The graph of the tangent function. And now that is the first part of the integral, right? The first part is convergent, right? This is convergent. And we are gonna work on the next part. The next part is the from 0 to pi over 4, right? This is from 0 to pi over 4 infinity, right? This one is also pi over 4, right? Because this is an even function. So if this part is true, then it means this part is true. This is an even function because of this fact. So this is also pi over 4. And after this, we can combine the sum, right? So it means the whole thing is gonna be convergent, right? That is pi over 4 plus pi over 4 is pi over 2, right? Convergent. Okay, and also is also similar to the previous questions. Turn the improper integral into limit notation and then go through the limit. Okay, that is question D. So we have done 4 of them here, and I think should I work on E, or should I move on to the next one? Actually, E is also very similar, except for replacing this with U. You're gonna do something to the denominator, right? Some factorization, and then replace that with U. And except for that, nothing is different. So maybe we should move on to question 2. Use comparison theorem to determine whether the given integral is convergent or divergent. Right? That is a lot easier. I think we don't need to compute that much thing. We just need to compare this with some known function. Okay, so the function that we're dealing with is this sine cosine thing divided by 2x minus 1. Right? So if we take this thing out, and then we want to change the numerator and the denominator to something that we're familiar with, we immediately think of that we can use the sine square plus cos square equal to 1, right? So the top can be replaced with 1 plus 2 times cos x, right? This is 2x minus 1. And we can drop this cos, right? Because this square is greater than 0, right? So we should drop this guy, right? And before dropping it, I need to ensure that everything else in here is positive, so we can make this greater than or equal to something else. Now we kind of look at the bounds here. The bounds here is from 3 to infinity, right? So x is greater than 3. Tells us that 2x minus 1 is greater than 5, right? Which is greater than 0. So we kind of have ensured that this is greater than 0. Denominator is greater than 0. So when we drop this trig function, we have greater than or equal to, right? So this becomes 0, 1 plus 0, drop it like that, right? And now the function becomes a lot simpler. And you can anticipate that this is a divergent integral of the right-hand side function here, but to be clear, we'd better drop something else to make that a nice form. So this is a negative one here, right? Negative one here. This is a positive thing, right? So when we drop the negative 1, the denominator becomes less than the previous denominator. And we know that for positive fractions, the smaller the denominator is, the greater the function is, right? So if we drop that, the denominator becomes greater, right? So the whole function becomes less. So this thing, chain of inequalities continue. So this is 1 divided by 2 divided by x. Right? And we clearly know that this is a divergent thing by the p-test. Right? So now we fill in the details after this. This is for greater than 0, for x greater than or equal to 3. And now we say that the integrand function is continuous on this integral 3 to positive infinity, right? And our comparison function this 3 to positive infinity 1 over 2x, right, dx, it's divergent by the p-test specifically at p equal to 1. So by the comparison theorem, right, we have that this whole thing sine square x plus 3 cos square x divided by 2x minus 1 dx, it's divergent because this function is even greater than a divergent function, right? And we make sure that we are using the positive side to do the comparison, right? So this is going to be divergent. And the technical stuff here is how do we change this expression to something that we are familiar with, right? And that takes experience, just like the substitution part, right? What the substitution should be, what the u should be, and that depends on situation. So that is our question A, divergent. And now let's move on to question B. That is this guy here. Okay. So now the function we need to work on is this guy. I take it out. Take it out. Right. And what can we do about this? Right. We know that x is from 2 to positive infinity, right? From 2 to positive infinity, the top is going to be greater than 0, right? This bottom is going to be, this is greater than 2, so this is also greater than 0. This is also greater than 0. So the whole thing is going to be greater than 0, right? Greater than 0. So we can consider dropping this term because it's complicated, right? So if we drop that, the numerator becomes less, right? This is a positive thing, right? Becomes less, then the whole function becomes greater, right? So indeed, if we drop this, this becomes less than or equal to 5x, right? This is 0 plus 4x squared, right? So in this direction, we should prove that the function is convergent. So the original function is less than a convergent function, so it's also convergent. So let's see if we can do that. Now we want to continue to drop things, right? So this is already a power function, so there's no need for that. So factor out the coefficient, that is 5 over 2. This is x to the 1 over 2. This is x to the 2, right? Together that becomes 1 over x to the 3 over 2, right? Now so make sure that this is greater than 0. That is very important. Like I said, this is greater than 0 at the very beginning, right? So now we have that this function is less than our comparison function, right? By the p-test, this is gonna be convergent, right? And then now you can so be more specific. That's when x is from 2 to positive infinity. Okay. And so now by the p-test, this is p equal to 3 over 2, right? Greater than 1. The integral from 2 to positive infinity 5 over 4 times 1 over x to the 3 divided by 2 dx is going to be convergent. Apple Pencil is dead, so wait a few seconds. Charging at 2%. So this is convergent, right? And since the original function is continuous on this interval from 2 to positive infinity, we can apply the comparison theorem, right? Because of that. So we can apply comparison to conclude that the integral of this x ln x plus 4x squared, it's also convergent. Okay. So basically, same as the previous question, right? You find a comparison function, and this is going to be less than that comparison function, and it's convergent. And the thing that we need to pay attention to is we always need to have the condition that the original function is continuous on that integral, on that interval. So just a routine to do, but that is important. Otherwise, we cannot use the comparison theorem. Okay, so that is the first assumption, the very first assumption of it. We need to always mention when we do this. Missing this, that is not going to be okay. Okay, so that is our question B, right? Convergent integral. And now maybe move on to the next. And I'm gonna leave this for you. Maybe move to the third part. Right. Eliminate the parameter to sketch the given curve. Indicate the direction in which the curve is traced as the parameter increases. So first one here should be very easy. Okay, you can substitute t, right? Solve t in this case. For example, this guy here, right? This guy is t equal to y plus 3 divided by 2, and you kind of plug this into here, right? So x is gonna be 4 times y plus 3 divided by 2 minus 5, right? Which is 2y plus 3 minus 5, right? That is 2y plus 6 minus 5, which is 2y plus 1. So x is equal to 2y plus 1 is a straight line, right? A straight line. Maybe write that as y equal to x minus 1 divided by 2. That is y equal to 1 over 2x minus 1 over 2. Right? The graph is kind of like that. Minus 1 over 2 here. This is 1 over 2x. And this is going to be 1 over 2. Okay. And now we're gonna find out from where to where the curve is traced. So when the parameter increases, you see that here, right? When t increases, x increases, right? So when x increases, the curve should be traced from left to right, because when that's what happened when x increases. So it's in this direction, from left to right, right? Traced. Okay, very simple. Just take a look at how the x, y coordinate are changed when t increases. That is question A. And now I'll move on to the next question, question B. This question, the range of t is given, otherwise it's going to be by default be from negative infinity to positive infinity, so like the previous question. So this is given, right, from negative pi to pi over 2. So we should sketch the graph according to the range of t. But firstly, let's eliminate the t. Okay, so we have the sine thing, cosine thing here. And the typical thing to do is to use that square, sum of square equal to 1. So we're going to create cos square and sine square in this case. Okay, so for this, we turn that into x minus 1 equal to negative 2 sine t. And we square both sides to have x minus 1 square equal to 4 sine square t, right? So we created that sine square. And for this one, that's my y minus 3, move to the other side, that's cos t. And square both sides, that is 4 cos square t. And then we're gonna add this 2 up, right, plus, right? So we have x minus 1 square plus y minus 3 square equal to this 4 this thing plus 4 cos t, right? Which means that this guy now is equal to 1. It's equal to 4. Right? So when that is equal to 4, that means we have a circle with a radius 2, so 2 squared. And the center of the circle should be at this point, 1, 3. So center is 1, 3. 1, 3. Okay, so that is very simple. Having this here. So center 1, 3 is about here, 1, 3, right? And the radius is going to be 2, right? So it's going to be like that. That is our graph. Maybe here. Well, but keep in mind that we have the range of t, so we should trace our graph according to the range of this t. Okay, so now let's trace the curve. When t is equal to negative pi, you see when t is equal to negative pi, we have this negative sine pi, which is 0, right? So when t is equal to, let me write it here. When t is equal to negative pi, we have x equal to 1, 1 minus pi sine pi is 0, and y is equal to cos pi, that's negative 1, right? Negative 1, so negative 2. Y is also equal to 1. So our starting point is here, right? This is 1, 1 to start. And when t is equal to pi over 2, we have x equal to 1 minus 2 times sine pi over 2, that is negative 1, right? And y is equal to 3. Okay, so our terminal point is negative 1, 3. Negative 1, 3, that is here, because the center is 1, 3. Okay, and we know that for this trig function thing, we should do that counterclockwise, right? So trace from this, right, towards the terminal point counterclockwise, right, in this direction. And for the other part, we should remove it because that is not in the range of t. Right? So remove it, the rest part here. Okay. So we only have 3/4 of the circle here, right? And the direction is counterclockwise from 1, 1 to this negative 1, 3. Okay. That is. I hope that's not too confusing, right? So that is our question B. Okay, and I have the last 2 minutes. I don't think I can do anything more, so I will see if you guys have any questions. Any questions?